Now that you see the notes, is there anyone who needs a copy? Okay. All right, so we talked about this new section here. It's on measures of spread. We talked about numbers that described how spread out the data is, right? And the first set of numbers that we talked about were the mean and the standard deviation. And we talked about this idea of going like within 1 or 2 or 3 standard deviations away from the mean, okay? So for example, within 1 standard deviation of the mean would be taking the mean, adding 1, subtracting 1 standard deviation above and below the mean, and we would get, well, this shaded area here, okay? We could also add 2 or 3 standard deviations away from the mean, and we just be further and further away from the mean, okay? So since this specific shape of a graph is very widely used in statistics, we call it the normal distribution because it's so normally used. We actually have like percentages that we know what percent of the data lies within 1 or 2 or 3 standard deviations from the mean, okay? This is so important that it's actually named the empirical rule. And what's special about the empirical rule is first, it only works for that bell shape or normal distribution, okay? And it tells us like exactly what values are within 1, 2, and 3 standard deviations from the mean, okay? So we did some examples on how to use the empirical rule. Then we talked about Chebyshev's inequality, which kind of was very similar to the empirical rule, but instead of only working for normal distributions, it can work for any shape. So even something that looks like this, okay? And we also said something about Chebyshev's inequality was instead of using the word approximately, well, Chebyshev's uses at least or more than, meaning the empirical rule is a little bit more accurate than Chebyshev's inequality, okay? Well, we answered a question on that, and then, then we moved on to a different topic. Okay, so the last thing in this section, in measures of spread, there we go. There's this thing that we want to talk about called the coefficient of variation. And before I talk about the coefficient of variation, I want to make it very clear what the standard deviation tells us if it's small or if it's large, okay? So let me just talk about the standard deviation real quick. Okay, so let's say you found the standard deviation and it was a really big number. So it was very large. Okay. Would that mean the data is more spread out or really close together? Any ideas? If the standard deviation is really large, it actually means that the data is really spread out. Okay, and it kind of makes sense because if I go out 1 standard deviation and 1 standard deviation is really big, then 68% of the data is going to be in that large area, okay? So if you have a large standard deviation, that means your data is really spread out, okay? And if your standard deviations are really small, then your data is going to be really close together. Okay, so just to keep in mind what the standard deviation means, okay, large means spread out, small means close together. I'm going to throw a new definition at you that doesn't get used too much in statistics, but it is really useful when you want to not just focus on the mean or just the standard deviation, but a combination of the two, okay? We call it the coefficient of variation, CV for short, and we can find it by doing this. We can take the standard deviation and divide the mean. Okay, so standard deviation over the mean. Okay, so let's just take a look at the formulas. Standard deviation is on top, which means whatever the standard deviation does, the coefficient of variation also does. Okay, so let me just ask you something. If you find the coefficient of variation using this formula and you get a really large number, okay, does that mean that the data is more spread out or really more close together? I think I heard spread out, right? Because, and that's actually right. So let me write that down. If you do this coefficient of variation, you get a really big number it also means that the data is really spread out. Because look at the formula, the coefficient of variation literally has the standard deviation on top of that formula, right? So that means if you have a really large number up top, then that means the coefficient of variation is also going to do the same thing, okay? So if you have a large coefficient of variation, you have spread out data relative to the mean, okay? And if it's really small, you're gonna have close together data. Okay. So why don't we take a look at applying this coefficient of variation? Let's try and figure out what's actually going on here. And in example 3, we're talking about the National Weather Service, okay? So they took a bunch of records and, oh my gosh, this question has a lot of numbers being thrown around at me. Whenever I see a word problem and there's like 50 billion numbers in here, I like to make a little chart, okay? Just write down what's going on, okay? So it says the annual precipitation, so let me write that, the annual precipitation in Atlanta, Georgia. It says it has a mean of 49.8. All right, mean 49.8 and a standard deviation of 7.6. Standard deviation 7.6. Okay. After that, it says the annual temperature, annual temperature has a mean of 62.2 degrees Fahrenheit and a standard deviation of 1.3. Okay, so now that I wrote everything down, now the question doesn't seem too bad because all the numbers are in order. Next, we want to compute the coefficient of variation for both precipitation and for temperature. Okay, well, why don't we go ahead and do that? If I were to find the coefficient of variation of the annual precipitation, well, what would I divide? What would go on top? Perfect, 7.6, because it says the standard deviation has to be on top. So 7.6 definitely has to be on top, which means the mean would have to be on the bottom. Okay, so once we divide this together, you should get 0.153. Okay. And then, well, now we have to do the coefficient of variation for the other one, right? So coefficient of variation of annual temperature, same thing, standard deviation goes on top, 1.3. The mean goes on the bottom, 62.2. And when we divide this together, we get 0.021. Okay, so all I did is I found the coefficient of variation for both of these two values. Which one's bigger, the precipitation or the temperature? Precipitation is definitely bigger. So which one of the two is more spread out relative to the mean? Precipitation, right? Because a larger coefficient of variation means we have more spread out data, which means relative to the mean, the annual precipitation is more spread out. At least relative to its mean. Okay, and when you think about this question, it kind of makes sense that precipitation would be more spread out than temperature, right? It seems like temperature fluctuates less than precipitation. So this answer actually does make sense, at least in my head. All right, any questions on the coefficient of variation? All right, then this actually ends this set of notes. So I guess we have a new set of notes to talk about. Okay, so we are starting this new section. It's called measures of position. I'm going to say mathematically, this section is probably going to be the hardest of all the sections. I think there's a lot of different calculations being thrown around in this section. There probably is going to be one more section that's a little bit harder than this one, but I would say mathematically, this is the hardest section. We're going to be talking about this thing called the z-score, which confuses a lot of people for some reason, which kind of blows my mind. The z-score is honestly a very simple concept. I'll try to explain it the best I can, and we'll talk about maybe why it might be more complicated than you may think, okay? So what I have here is I just took a picture of the textbook, This is a picture of the empirical rule. Remember that 68, 95, 99.7 rule that only works for the bell-shaped distributions. We have within 1 standard deviation, 2 standard deviations, and 3 standard deviations of the mean being shaded here, okay? Now, instead of focusing on the percents, what I want to focus on are actually the x values on the x-axis, okay? And I'm going to assign some scores to them, okay? Let's just start at the mean. Remember, the mean in a symmetric distribution is always in the center of the set. So I'm just going to give that a z-score of 0, okay? Now, if I go 1 standard deviation up, so I take the mean and add on 1 standard deviation, I'm going to give this one a z-score of 1, okay? And even if we go 3 up, the z-score for this one is going to be 3. Is someone catching all of this? Can anyone describe what a z-score is telling us? Okay, yeah, the amount of standard deviations you are above the mean, right? So if I'm 1 standard deviation above the mean, the z-score is 1, right? Can someone guess what like this one would be minus 2 standard deviations? What would this z-score be? Be 2, but well, this is also z equals 2, right? So what do you think this makes this one different? Yeah, it's going to be negative 2, right? So if we're below the mean, we have a negative z-score, right? So if I went negative 3 standard deviations away from the mean, z would be negative 3. Okay, so the sign of our z-score tells us if we're above average or if we're below average. Okay, the z-score can be even more precise here. Even scores like this x value here. Okay, I can give that a z-score of 0.3. Right? So we can have a decimal z-score by saying, okay, if z is 0.3, we're 0.3 standard deviations above the mean. So between 0 and 1, okay? Or we can even be, I don't know, z equals negative 1.4. Gosh, that is a bad 1.4. There we go, okay? So a z-score can be any value, and it just tells us how many standard deviations we are either above or below the mean, okay? Any questions on what a z-score is so far? Okay, so here is the fun part, okay? I put a definition of what a z-score is. You don't have to memorize the definition. I just want you to know what it means, okay? We actually have a formula for the z-score, okay? So here's the formula. To find the z-score, you're going to take any x value that you're interested in, so any data value. Okay, you're going to take that data value and you're going to subtract off the mean. Once you're done subtracting off the mean, you're going to divide that whole number by the standard deviation. Okay, so this is a formula that gets used a lot in statistics. I do want you to memorize this formula. Okay, so make sure you know what this formula is. We will be using it throughout the rest of the class. And just make sure you know how to use the formula as well. We'll talk about that in the next page. Okay, let's go on to actually using the formula. All right, in this example, we have a teacher, and this teacher is giving 3 versions of a test. Okay, all the versions are normally distributed, okay? Now, since we have a lot of numbers thrown around, I have a little chart to have us kind of organize our numbers in different ways so we're not looking at this big mess of numbers here. Test number 1 has a mean score of 66 and a standard deviation of 4. Test version 2 has a mean of 66 and a standard deviation of 2. And test number 3 has a mean of 72 and a standard deviation of 6. Okay, so I just organized all the information so I don't have to go back into the question to figure out what the numbers are. So let's see this one. We have Jamie. Jamie received a 70 on test version number 3. I want to know what Jamie's z-score is, and I want to know what that actually means in terms of the standard deviation and the mean. Okay, so I know I have this formula. We have z equals x minus mu over the standard deviation. You have to memorize that formula. Okay, And if you can work with formulas really well, you don't have to do this step, but I'm going to do it because if I don't do this, I always mess up. So I'm just going to make a little chart here. I'm going to write all the different variables in this formula, all the different letters. Okay. If Jane received a 70 on the test, is 70 z, x, mu, or sigma? It's got to be x, right? Because, well, first of all, the question is asking for the z-score, right? So it can't be the z-score if we don't know what the z-score is. And mu and sigma, they represent the mean and standard deviation. So 70 has to be x, okay? Now, mu and sigma just represent the mean and the standard deviation. Looking at test version 3, the mean is 72 and the standard deviation is 6. Okay, so now I have everything written out. Let me just plug everything into my formula and see what happens. So we have z by itself, because I don't know what that number is. X is 70, mu is 72, sigma is 6. Okay. So now that I've plugged in all the formulas, I don't actually have to solve the equation because z is by itself. All I have to do is just subtract the numbers and divide, right? So, oh, didn't mean to do that. So 70 minus 72 is -2. I always recommend doing each step and writing it down instead of doing the whole thing in your calculator, because I always mess up if I do that. And 2 divided by 6 is -0.333, right? Okay. So what we just did is we figured out the z-score, Jamie's z-score, okay? And what does that actually mean? Did Jamie score above or below average? Below average, right? Because a negative z-score means you're below the mean, okay? And the number actually tells us how below average he scored, right? It's not like he scored way below average. He only scored minus 0.33 standard deviations below the mean, right? So it's not like he did completely bad. He just did below average very slightly, right? So I'm just going to write out what this means here. Okay, so if I were to interpret this, I would say this. Jamie scored 0.333 standard deviations below the mean. Okay, that's how I would interpret this result. All right. Any questions on how I did number 1? Okay. Let's make things a little bit more complicated, okay? Let's say we have Anna. Now, Anna stored a z-score of -1.5. This time, I don't want to know her z-score. I want to know her actual test score, okay? So using our formula, I know that I need a z, an x, a mu, and a sigma, okay? Does -1.5, is that a z-score or an x value? Z-score, right? Because it says the z-score was -1.5. That means z definitely has to be -1.5, okay? I don't know the test score, so I'm going to put a question of the x, okay? And if we're working with test version 1, just peeking up at the chart I made, the mu is 66, sigma is 4. Okay. So I'm going to take my formula, the x minus mu over mu, or x minus mu over sigma. I'm going to plug in all the numbers that I know, right? We have -1.5 for z, x is by itself, minus 66 over 4. Okay. Now, here's where things get a little bit tricky. I want to get x by itself, right? X is mixed in with the 66 and the 4. Should I undo the 4 first, or should I undo the 66 first? The 4 first, right? And if you're ever confused which one to do first, what I like to do is I like to think in my head, okay? I know that x is what I want to find, okay? If x was, I don't know, like 100, okay, if it was just some number, well, if I plug this into my calculator, the first thing I would do, I would first subtract 66, right? And I would then divide by 4. That's what I would do if I were like calculating this in my calculator, right? So if I want to undo this, well, you just do the opposite. So you go up, you first undo dividing by 4, and then you undo subtracting by 66, okay? So why don't we do that? How do I undo dividing by 4? Multiply, right? The opposite of division is multiplication. I'm gonna multiply both sides by 4. Also cross out that 100 if you want to get confused later on. Okay. Now if I do something on one side, what do I have to do? What do I have to do on the other side? Same thing, right? So I have to multiply this side by 4 as well. Okay. 4 times negative 1.5 is negative 6. Okay. And then on the right hand side, it looks like the 4's cancel out. So top and bottom cancel out. And we have x minus 66 on the right hand side. So we got rid of that division by 4. Good. Okay, so we undid that part. Next, we have to undo subtracting by 66. What's the opposite of subtracting by 66? Adding 66. Good. So I'm just going to take 66 and add it on both sides of the equation, right? Okay. So on the left-hand side, negative 6 plus 66 is 60. And these guys cancel out. So we're just left with x on the right-hand side. Looks like we got x by itself. That made 60 Anna's test score. Okay. Any questions on solving the equations here? All right. If you flip the page, I have an example for you. I have Bob's z-score, okay? First of all, I want you to figure out, okay, is this a question like number 1 where I'm just plugging things in? Or is it a question like number 2 where I have to solve? Okay, so that's the first thing you need to do. The next thing you have to do is, well, find the answer, right? So I'm going to give you a few minutes to work on number 3, and we'll be back in a little bit. All right. Looks like everyone's on a really good track here. All right, so number 3, I got Jordan to write up his answer. Do you want to take us through your steps, Jordan? Mm-hmm. Mm-hmm. Perfect. Very nice steps here. Do we have any questions on what Jordan did here? All right. Okay, so very nice job here. This question was very similar to the second question, not the first question, because we had to solve the equation. I think the first question is pretty straightforward though. Let's move on. All right. We're going to talk about a different type of number that we haven't talked about before. We call it the percentile. Okay. And well, does anyone know what, or has anyone heard the term percentile get thrown around? Kate, yeah. Has anyone taken the SAT? Yeah, usually your result, your score is going to be a percentile. I'll give an embarrassing story that I have. When I got into grad school, I had to take this thing called the GRE, and the GRE has subject tests, and they have a math subject test, which is really hard. Now, I took the math GRE, and my percentile was, I got the 30th percentile. Is the 30th percentile, is that good or is it bad? Who says good? Who says bad? All right, 30th percentile is very bad. 30th percentile is a very bad score. What it means is that I only did better than 30% of the people who took the GRE, the math, the GRE, which is very sad. That's very embarrassing, but it didn't really matter. I didn't submit my GRE to my grad school and I still got in. So hopefully you guys are better at taking standardized tests than me. Anyway, so the idea of a percentile is it basically is a score or a data value that represents something like that separates the lower like 80% than the higher 20%, right? So it kind of separates percents of the information. If you ever take a standardized test, you really want like the 99th percentile. That would be an awesome score because you would do better than 99% of everyone else who took the exam, right? So getting a high percentile is a very good thing, okay? Now, this is the textbook definition of a percentile. I don't like the textbook definition because it throws letters in here and there's a lot of letters to keep in track of. So what I'm going to do is I'm going to give an example, go through how I would find the percentile, and it might not make sense at first, but once we do an actual example, it'll make a lot more sense, okay? So let's say I wanted to find, I don't know, the 15th percentile, okay? So that means I want to figure out what number separates the lower 15% of scores and the higher 85% of scores, okay? So I want to find that score that 15% did less than they did, okay? Here's what I would do. First, I would change 15% into a fraction, okay? So I get that fraction, and I would multiply that fraction by the total amount of data values, okay? Now, there's two options. If you do that and you get a decimal, you're going to round that decimal up to the nearest whole number, okay? If you didn't get a decimal and you got a whole number, you're going to take the average between that answer and the next highest number. If that doesn't make sense, the next example is going to show you what this all means, okay? Let's do a little example and see what happens, okay? Here we have a bunch of numbers, okay? And with these numbers, I want to find the 11th percentile, okay? When you find the 11th percentile, the first thing you ever want to do when you do these questions is to write the numbers in order. This is very similar to the median. It actually is exactly the median, but we'll talk about that later, okay? So first we're going to write the numbers in order. A lot of you can do this in your head. I am very bad at doing things in your head. If you ever get confused on drawing or writing numbers in numerical order, my advice to you is to just draw a stem and leaf plot, okay? So if I were to make a stem and leaf plot, I have numbers in the 50s and in the 60s. Those would be my stems. And I would just read through the numbers and write them wherever they belong. We have a 51, 54, 55, 56, 58. We have two 60s, a 61, 3, 2, 8, and 2. Okay, so I just went ahead, I drew a stem and leaf plot. This isn't a complete stem and leaf plot because the rows aren't in order, but this helps me write all the numbers in order because now I kind of separated half the data, so I kind of know where they fall. Okay, so I'm going to go ahead, write these numbers in order. We got 51 as our lowest number. We've got 52. We've got a 54, a 55, 56, two 58s. Moving on to the 60s, we have two 60s, a 61, a 62, and a 63. Okay, so all I did is I went through the numbers and I wrote them in increasing order. Okay. The next thing I'm going to do is I'm just going to assign numbers to each of my numbers. And if that doesn't make sense, let me go ahead and do it. 51 is my lowest number, so it gets a 1. Second lowest number gets a 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. And what this is going to do is it makes it really easy to look at the numbers and be like, what's the 7th lowest number? 58. What's the 11th lowest number? 62, right? So it makes it really easy to go and be like, okay, I know what the second number is, I know what the 9th number is, and so on. Okay. Once we're done doing this, let's follow these directions and see how we can find the 11th percentile, okay? To find the nth percentile, change that percentile into a fraction. So first thing I'm going to do, I'm going to take my 11% and change it into a fraction. What's 11% as a fraction? 0.11, perfect. If you ever get confused, just divide by 100, you'll get that decimal. Okay, next it says, then multiply your fraction by the total number of data values. So take that fraction. What number am I going to multiply 0.11 by? 12, right? Because there's 12 data values. So just take that number and multiply it by the total. Okay. All right, 0.11 times 12 gives me 1.32. Okay. Here's where things get tricky. Okay. If we get a decimal, round it up to the nearest whole number. Right now, for this specific question, I want you to forget about everything that you've ever learned in math. Okay. Remember, in math, we always learn about rounding, we would round that down to a 1, right? For percentile questions only, I'm going to want you to round this up to 2. Okay, so even though 1.32, it seems like it should round to 1 because 3 is less than 5, you always round up these decimals to the next highest number. Okay, it's just a convention in statistics. Some guy just thought, oh, I guess we're going to round things up to the next number instead of rounding like we normally do. This is just how percentiles go. So remember, always round up to the nearest whole number. Okay, so if I want to find the 11th percentile, it's pretty easy. Since I got 2, look for the second number. 52 is the second number. That's my 11th percentile. So the second number is 52. That's my answer. Okay, that is the number that separates the lower 11% than the higher 89%. All right. Any questions on how I got this answer here? Yeah. Yeah. So let's see. So first we did 11% and we converted that to a decimal, right? Then I took the decimal and multiplied it by the total number of things. So that number is 1.32. You round that, whatever number you get, you round it up to 2. And that's how we got the 2. Yeah. So it's like 1, 2, 3, 4 steps. Yeah. We'll do tons of examples on these. So I feel like you just kind of have to get used to doing it. There's so many different steps and there's so many different places where you can mess up. But I promise by the end of this section, we'll be experts on this. Yeah. So you're like, oh, can we just get 2? I like to see the steps just because like on a quiz, I would want to know where it came from. If you did a lucky guess, I'd probably mark it right, but there's a chance you might do a unlucky guess, right? All right, let's go to the next example. This one's slightly different, okay? This time I want to find the 75th percentile. Well, we're using the same data. I already wrote the data in order, so we don't have to worry about that, okay? I'm gonna first take my percentile, 75, and convert it into a decimal, right? So 0.75. So that's the first step. Then you're gonna take your decimal. What am I gonna multiply 0.75 by? 12, good, because 12 is the total number of things. Okay, and when I multiply that together, let's see what I get. We get 9. Okay, so this time when I did the multiplication, I didn't get a decimal. I actually got a whole number. Okay, whenever you get a whole number, things get a little crazy because we don't actually round up this time. Okay, what you do when you get a whole number is you're going to look for the 9th number, the one that you found. You're going to find the number after it, the 10th number, and write those down. So the 9th number, taking a peek at my data, the 9th number is 60. Okay. The 10th number, looking at my data, was 61. Okay. Write those two numbers down, and the 70th percentile is going to be the average of the two. So you're going to take the average. Very similar to finding the median, right? When you take the average of two numbers that you found, okay? The average of these two numbers, remember, add them together, divide by 2. The average is 60.5. That's the percentile that you're looking at. Okay. Any questions on what I did for example number 3? Okay, so percentiles, you always change the number to a decimal. You always multiply the decimal by the total number of things. If you get a decimal, you round up and find that number. If you get a whole number, you're doing the average of that number and the number above it, okay? Okay, that was a lot. We do have an example after it. Okay, how about this? I'm gonna give you like 3 minutes to work on these. I don't know if we'll actually get to finishing this example, but I do want to give you some time to work through some of these examples on your own. I don't know if we're actually gonna get to finish this, but how about this? First of all, I'm gonna write the numbers in order. Do a small check on your notes and make sure that these numbers are written in order. We've got 2, 5, 9, 10, 10, 16, okay? And of course you can number those numbers too. Okay. I actually didn't even get to this in my last class, so how about this? We'll pick up on this next class. If you want to check your answers, the answer for A should have been 9, and the answer for B should be 9.5. We'll talk about how to get these answers on Wednesday. So if you're confused about why those answers are the right ones, we'll talk about that on Wednesday.